So not yet.
Not yet. Okay, 2 minutes maybe. Can you see now?
No, sir.
I see. Wait a minute. So you said just 1 minute. Ah, can you see now?
Yes, sir.
Okay, very good. Terrific. So shall I enlarge the screen now? I mean, the view.
Sir, sometimes there is a problem that like if you go full screen, the slides don't change
Oh, I see, I see. But
in
this is good.
presentation. So,
This is good.
yes, if you can zoom in without going to full screen, then that would be nice.
Ah, okay. Just 1 minute. Huh? Just 1 minute. How about this? Is this better?
It seems like the slide is still of the same size. Can that be enlarged?
So now, what do you want me to do?
Okay, sir. Can you
How
just?
about this?
Yes, sir. This is much better.
Good?
Yes.
Very good. I'm not very expert in all this, okay?
No problem, sir.
But it's okay. This is, the screen is good?
Yes, sir.
Okay, good. Very good. So how do you usually conduct this? I mean, do you have questions at the end? And
Yes, sir. So usually people type their questions in the chat, and they can be taken at the end.
yes, so what I suggest is that one of you really monitor all that, uh, just in case so it's at the end actually. There are no questions during the talk.
Yes, mostly people
Okay.
don't ask during the talk.
I think that
If
will be
there's
good,
something
you know why?
urgent,
Yeah, yeah. Well, I mean, it will be best to have it at the end because, uh, yeah, how do I say? Because the talk then can go on for a very long time. I don't have a problem, but given the level of the material, and I've tried to somehow uh, make it as simple as possible. But anyway, let's see.
right? And sir, can we wait for just 5 minutes
Sure.
for more people to join?
Yeah, yeah, not at all. No problems. Yeah,
And can we record this talk?
of course, no problem.
Thank you, sir.
Yep.
All okay?
All okay.
You're connected, you're presenting?
Yeah.
Okay, good. I'll secure this.
From here, what will you see?
Send me the link and I'll join.
Okay. Could you join? Could you join?
Okay, now before we
Yes.
begin, I would like to introduce Sir to our audience. Our speaker, Professor Spenta R. Wadia, is the Infosys Homi Bhabha Chair Professor at the International Center of Theoretical Sciences and Emeritus Professor at TIFR. He is the founding director of ICTS TIFR, a unique institution in India involved in furthering the boundaries of fundamental research and science education, emphasizing that science is one story. He has made basic contributions to quantum field theory, statistical mechanics, string theory, and black hole physics. He is an alumnus of St. Xavier's College, Mumbai, IIT Kanpur, the City University of New York, and the University of Chicago. Now I would like to hand over to Professor Spenta to begin the talk.
Okay. Thank you very much for the kind introduction. It's a great pleasure for me to be here and talking to you. I have learned a lot preparing this talk, as you will see. Okay, so today we are going to talk about black holes and Hawking radiation. I exactly don't know the spectrum of preparation of the students who are going to listen to this, so I have designed this talk in such a way that there is something for everybody to take home. Okay, all right. So let's start with very elementary. Just see how I'm not able to change my slide. Just a minute, I'm not able to change my slides. Okay, thank you. But this is not in presentation mode, so let me just go to presentation mode. How is this now? Hello?
It is better, sir.
Better, very good. All right. So let's start at the very beginning. So as you know, Galileo in the 16th century, who was a pioneer of the modern scientific method, discovered a new law of gravity. And this new law is something which you know very well. It says that gravity acts in the same way on all bodies. They all fall in the same way, independent of their mass. And this is called the equality of inertial and gravitational masses. So it's a very fundamental law of nature, this one. And it has been verified experimentally to 1 part in 10 to the 13. Okay, so now let's jump historically to Isaac Newton. So you know about this. Newton formulated the laws of motion in terms of the flow of time, something that looks so trivial today, but which took a long time to understand. And he has his very famous laws of motion. Can you see my cursor? Hello? Hello? Hello?
I can't
Hello?
see your cursor, sir.
You cannot,
No,
or you can?
no, I can't.
Okay, okay, fine. All right. Okay. So anyway, so I'll just do without it. So you all know about Newton's law of motion. So let me just go on. This is the beginning of our subject. And then comes the famous Newton's law of universal gravitation, which also you all know. But it was a law which had a instantaneous interaction between the two bodies. Okay, I just wanted you to note that. And that is a problem which Newton himself had recognized, and that's quite amazing. Okay. Then towards the a couple of hundred years later, when the laws of electromagnetism were being formulated, the idea of the electromagnetic field was introduced by Faraday and developed further by Maxwell. And you know this history also of electromagnetism. The key point here is the fact that there was no action at a distance. The idea of action at a distance was resolved in electromagnetism between two charges. So I just wanted to make this point because this is a crucial point actually, which ultimately remedies the law of gravitation of Newton in the theory of Einstein. And again, this locality problem is the one that we will encounter towards the end of the talk. Okay, so now enter Einstein and special relativity. You all know about special relativity, so this is just a slide to give you a glimpse of it. The basic point is the speed of light is the same whether you run towards it or away from it. That is the key point. And based just on this statement, you can derive the entire theory of special relativity. In some sense, space and time have to adjust themselves to ensure this happening. Okay, and then there is one very important intellectual leap due to Minkowski. Hermann Minkowski was Einstein's teacher, that he understood relativity in terms of geometry. Okay, and of course that played a very important role in the development of the general theory of relativity. All right, so Einstein had a couple of puzzles. That Newton's law of gravity was in conflict with special relativity. And he was worried about why only special relativity. Why should it be that the laws of nature should be invariant only under reference frames which are moving at constant velocity with respect to each other? Why? We questioned these two things. All right, and the reason was that the force of gravity acts instantaneously, as I mentioned before, and that's not consistent with special relativity, in which the speed of light is finite. And Einstein would like to have the force of gravity communicated at the speed of light, very much like the electromagnetic theory of Faraday and Maxwell, which I mentioned. And also, that's, as I said, special relativity is restricted to frames with relative constant velocity. But the laws of physics must be valid in any general frame, including accelerating reference frames. So these are the motivations for Einstein to think about coming up with the general theory of relativity, which took him around 15 years to develop. Something like that. Okay. So these puzzles were resolved by Einstein. And in 1915, he came up with the general theory of relativity, which basically summarized in what I'm saying, that the gravitational force felt in a small neighborhood of space-time is understood in terms of acceleration of the frame. And the force of gravity is not instantaneous. This is what is called the principle of equivalence. Okay? Einstein called it the happiest thought of his life, or something like that. And then the second point is the simple linear mixing of space and time by Lorentz transformations is now replaced by a nonlinear mixing called the general coordinate transformations, which are the gauge transformations of the general theory of relativity. So I just wanted to highlight some extremely important physical effects which are a consequence of Einstein's theory of general relativity. And so here I hope these animations work. We have two fellows, one on a lower floor and one on a floor which is slightly up, let's say on the 15th floor of a tall building or something. And the main point I just wanted to make here is that as you measure time nearer a gravitating body, time slows down, basically. And this can be proved in a very quantitative way in Einstein's theory of general relativity. So here is a very beautiful animation, which this is not, I didn't make all this. This was made by my friend Juan Maldacena. So you see the clock at the bottom is much slower than the clock at the top floors. Okay, and this effect is of course very relevant in the GPS that you use on your cell phones. But this is it's a deep and profound effect of the general theory of relativity. All right. Now, I just wanted to give you a pictorial idea of the equations of general relativity. So the equations of general relativity describe the shape changes of the geometry of space-time. It's as if space-time is like some elastic medium. And the distortions of this space-time, which are caused by massive objects, to which other objects respond. So in a curved space-time, an object follows a path that maximizes the time in the frame of the object. Okay, so this is the law actually of the motion of particles in general relativity. And here is again a small animation that illustrates to you that if you have a very large gravitating mass, let's say like the sun, it distorts the space-time around it like in a trampoline, and objects, lighter objects like the Earth or the other planets simply fall into the geometry. This is very qualitative, but it's very illustrative. Now, one little point here in general relativity, the space-time grid, this elastic stuff, this elastic medium I talked about, is very, very, very stiff. It's stiffer than the most solid stainless steel you can create in our factories. And the reason for this stiffness is precisely because this factor, Newton's coupling divided by the speed of light to the power 4, which appears in front of the right-hand side of Einstein's equations in the matter part, is so tiny that it requires an enormous amount of energy in order to shake this medium up. This is why it required the collision of two black holes to set off gravitational waves 1 billion years ago, which we observed a couple of years ago. This is the reason for that, this 10 to the minus 43. And on top, I've just flashed Einstein's field equations of general relativity, just for your, just like that. Even if you don't know these things, it's good to see a great equation. Okay, now we come to one of the most important consequences of the general theory of relativity, and this is the fact that general theory of relativity predicts black holes. It's a theory of gravity and it predicts black holes. And on the left-hand side, you see the picture of Carl Schwarzschild, who found the first exact solution of Einstein's equation, what is called the Schwarzschild black hole, whose geometry you see in this illustration over here. Within a few months after the publication of Einstein's theory of general relativity, Schwarzschild, who was actually serving in the First World War, wrote a note which actually contains the famous Schwarzschild solution, the first solution. Then black holes become inevitable in astrophysics due to the work of Subrahmanyam Chandrasekhar and Robert Oppenheimer. Just wanted to tell you that this photograph of Chandrasekhar with the volumes of the Principia and Newton's photograph on the top, you see this? I am the proud taker of this photograph. I took this photograph when I was in Chicago, actually. So I just wanted to tell you. Okay, so now let us try to see what happens. How do you describe a black hole spacetime? You will see that in this very simple illustration. The black hole spacetime is characterized by a surface called a horizon. A horizon classically is like a one-way street. Light enters it, light cannot get out. Nothing can get out of the horizon of the black hole once you are inside it. Actually. So this is a very peculiar type of space-time, and it's a characteristic of a theory in which all forces are really attractive. There's no repulsive forces like in electromagnetism, where like charges repel and unlike charges attract. Here, all charges, all matter interacts with an attractive way. So anyway, this configuration is formed, and it's a solution of Einstein's theory. And there are physical circumstances in which this is actually realized in astrophysical situations, as was illustrated by Chandrasekhar and Oppenheimer and Snyder. Okay, so this is another illustration. This is a interaction of two black holes, which I mentioned to you, swirling the very stiff space-time around it. This is an animation which illustrates the collision of two black holes that give rise to gravitational radiation. I just thought it's a beautiful animation to show you that black holes actually really exist. This was a rather indirect evidence, sort of quite direct actually, that this gravitational waves that were observed in 2015 were actually were caused by the collision of two black holes. They traveled more than a billion years to reach us. This is another illustration of the fact that black holes exist. This is it's a visual illustration of the image of the supermassive black hole taken by the Event Horizon Telescope. You'll see that, in fact, if you analyze this picture very carefully, the light that you see also is coming from behind the black hole because it is being sort of curved by the intense gravity of the black hole. These two slides I showed you to say that black holes exist. So what was the theoretical prediction? Sort of almost like 100 years later is absolute reality, experimentally verified. So it's great feeling, because otherwise we feel that we are working on systems which don't exist, especially people who work in string theory and quantum gravity. But now this black holes exist, so at least I am extremely happy. All right, so now let's get into a little bit of the geometry of the black hole and its consequences. What are the physical consequences of the fact that there exist black holes, and they're described by this type of metric. So this is the simplest metric which was originally discovered by Schwarzschild. This metric is characterized by what is called the horizon radius, RS, which is a surface actually. It's a null surface at which the first term in dt square really vanishes in this coordinate system. Okay, so it's called the horizon of the black hole. Now, this metric actually is very good only for when r, the radius over here, radius in quotes, is greater than the Schwarzschild radius. So if you look at the geometry of a large star or of any object, including the sun, for r greater than the Schwarzschild radius, it very correctly describes the space-time of that star. For example, the Schwarzschild radius of the sun is something like 3 kilometers only. So this is a very good description of the geometry of the sun beyond those 3 kilometer distance. Okay, so now this geometry was sort of worked on over many decades. People didn't really understand what it meant to put r equal to rs over here. So then you make coordinate transformations and you massage the system. Somebody realized that this is just a coordinate singularity, and you make a solution of the general theory of relativity which is regular at the horizon, because really there is no singularity there. Okay, the only singularity of the black hole is at r equal to 0, where the curvature, the real curvature of the space-time really goes to infinity. That's another matter. That's a future problem for us to tackle. But for the moment, we will be near and above the horizon. Okay. All right. So now there is a very simple way of describing this situation. It's called the Penrose diagram. The Penrose diagram basically encapsulates the geometry of the black hole. It's a precise mathematical statement. Okay, it's not just a cartoon. It's a precise mathematical statement in which you bring infinity by a conformal transformation to a finite distance. So this is the horizon of the black hole, which I have indicated. There's a singularity, and the star, the green stuff, actually, this green shaded region, is falling into the horizon. Okay, and then there is a space-time outside it. Okay, so this is a diagram that illustrates the formation of a black hole.
use the mouse, I might be able to see it.
Formation of the black hole. Okay, now one point is that this is a two-dimensional diagram, right? So in this diagram, only the time and r are somehow, only one direction of space and time are, twisted and turned around to make this type of plot. The other two directions, which are essentially a sphere direction, the theta phi in this omega 2 square, they just remain at every point. There is a sort of a sphere basically over here. So that's what this metric means. Okay. Now, if you have not seen it, bear with me. If you know what I'm talking about, then it's also trivial. Okay, let me go ahead. All right. Now we come to something very important. So now we come to the subject of black hole thermodynamics. Now, Bekenstein, Jacob Bekenstein, who was a student of John Wheeler, made a very profound and far-reaching proposal that black holes are thermodynamic objects. They are hot thermodynamic objects. Why? So he argued this beautiful argument. So, you think of taking some huge tank of hot water, and just throw it into the black hole. Okay? Now, before you throw it into the black hole, this huge object plus the black hole had a certain entropy. Now, black holes, I have not said have entropy, so the entropy is entirely in the hot tank of water. Now, once you throw the tank of water into the black hole, classically, according to general relativity and the solution of general relativity, it goes behind the horizon and disappears. You can't access it. This means that the entropy of the universe has decreased. But that contradicts the second law of thermodynamics. And this is what made Bekenstein suggest that black holes must have an entropy. And he suggested that the entropy of the black hole must be proportional to the area of the horizon. This is 4 pi rs square, okay, times a constant. That constant he cannot determine. He couldn't determine. In fact, in classical physics, you can never determine the absolute value of the entropy. So this is an arbitrary constant at the moment. So this is the famous law of Bekenstein, that the entropy of the black hole is proportional to the area of the horizon. And for the Schwarzschild black hole, it goes as the square of the mass of the black hole, right? Now, once you have entropy as a function of energy, you must have studied in your statistical mechanics class that if you take the derivative of the entropy with respect to the energy or the mass in this case, you will get a formula for the inverse temperature. So here it is. So if they have entropy, they have temperature. And this is the formula for the temperature. The constant B cannot be determined within classical physics. And that is where the whole story, the whole secret lies, really. And that was the great contribution of Stephen Hawking. So till now, we have been discussing black holes as classical objects. Now let us try to see what happens to quantum matter. Black hole is still almost classical. Okay? We're not talking of quantum gravity at the moment. What happens to ordinary matter, which is quantized, which has fluctuations, quantum fluctuations, in the presence of a black hole? So what are the consequences? I'll explain all this a little bit later, but this is the consequence. Hawking calculated this temperature. We already knew it has a temperature. And he calculated the temperature. And this is the famous formula of the temperature which was derived by Hawking. We saw it as 1 upon m, but we didn't know all these constants over here. And notice that the temperature is proportional to Planck's constant. Means it's a quantum mechanical effect. If there is no quantum mechanics, black holes have zero temperature. And here I've given you some little illustration. You go back, these slides I think you'll have. So when you go back home, you can work out the temperature of the sun. If you know the mass of the sun, which you should, and the temperature of a black hole of the size of the sun. That's what I mean, okay? Black hole with the mass of the sun, a black hole with the mass of the earth, a black hole which is 10 to the 18 kilograms, which is huge, but its temperature is very high, okay? So you can work it out because over here, the ratio of temperatures is inverse to the ratio of mass. So all these constants cancel. You can arrive at this very easily. Now, the important point here is that we have used, all right, alluded to the fact that I told you that the derivative of the entropy with respect to the mass gives you the inverse temperature, but that is the first law of thermodynamics. So the first law of thermodynamics then essentially is an encapsulation of these two fundamental formulas. And it says that the entropy of the black hole is proportional to the area of the horizon. This is the first illustration of a famous area law. And we'll see it plays a very important role later on also. All right. So here is a picture of Stephen Hawking with David Gross and Ed Witten, which we had taken during Strings 2001 at the Tata Institute in Mumbai. So yeah, that's a long time ago. Hawking is also no more now. So, and this is the tombstone of Stephen Hawking, and you can see the famous formula on the tombstone. It's quite amazing. This K over here is the Boltzmann constant. G is Newton's constant. C is speed of light, and h bar. So let me make one remark that this is a formula which contains all the three fundamental constants of nature. Please note this: h bar, speed of light, and Newton's gravitational coupling. So it's a very fundamental formula for that reason. Okay. All right. I won't elaborate on that. That's another talk. Let's go ahead. All right. So as I said, black holes are thermodynamic objects. Now you would want a thermodynamic object to obey the second law of thermodynamics, right? Black holes do obey the second law of thermodynamics in the sense that if you have two black holes and if you try to merge them, you get another black hole. Okay. And the area theorem is that the area of the horizon of the final black hole is always greater than or equal to the area of the horizon of one of them and plus the area of the horizon of the other. Another very important point, which is due to some beautiful theorems in general relativity, that if you take a black hole, you cannot split it into two black holes. Okay, that's another important area theorem. And these two area theorems of general relativity plus Bekenstein's proposal that the entropy is proportional to the area immediately implies the second law of thermodynamics for black holes, right? There's more to that actually. This more point is very important. That the black hole, you see, like all hot bodies, black hole will start radiating, right? So then you have to consider the system of the black hole and the stuff it is radiating, right? Which is what I have called S matter. It radiates matter. Radiates photons, gravitons, neutrinos, whatever. Now, so the total entropy formula has to change now, which is what I call the general entropy formula. So that is the entropy of the black hole, the geometric entropy due to Bekenstein, plus the ordinary entropy of the matter, which is in the radiation. Now, it took a long time to prove that this generalized entropy also satisfies the second law of thermodynamics. And I think the really solid proof was only given in 2010, just 10 years ago, by Aaron Wall. Okay, so this point I wanted you to keep in mind. We'll come back to this generalized formula later on. Now, the second point is in this slide is that a black hole forms in whatever way. You can throw easy chairs, collision of gravitational waves, collision of high energy particles producing black holes. But according to Hawking, I'm sort of anticipating myself, they always evaporate in the same way. Whichever way it is formed, whatever goes into it, in the end, there is only thermal radiation. And that is, in a colloquial sense, information loss. Okay. There is no memory of the initial state. And I think one of the achievements of recent times is to quantify this statement in a very precise mathematical way in terms of what is called, as I will explain, the von Neumann entropy of a closed system. Okay, so this is a very important slide. This I took from a review article by Almaeri and collaborators, which is very, very recent. It's a good review article, but it's a little technical. I mean, so you need to be working in the subject to understand it completely. So we start in figure A, which is the black hole. Okay, so it's like a trumpet. The front part is like the flat space time. Okay, and the red ribbon is the horizon of the black hole. Okay, so you fall inside the trumpet. Now, this a black hole has been formed at certain time t equal to 0, and slowly it starts Hawking radiation because it's hot. Okay, so it radiates from the neck, and the radiation spills out and goes away. Okay, so that's figure number B. That continues to happen. Okay, and finally, the whole black hole evaporates. So the final state is just flat space-time plus the radiation. So you started with a black hole, and you ended up with flat space-time plus radiation. The right-hand side is a Penrose diagram, actually, that explains this phenomena. I mean, that is more quantitative in some sense. That you again have this falling star, and there is a singularity. It falls into the horizon, forming a black hole. And when the black hole is formed in the vicinity of the horizon, you have pair of Hawking particles being sort of created. Now, why does this happen? It happens because, for example, in theory of electromagnetism, that if you have a time-dependent electromagnetic field, which is quite strong, then you can pair produce elementary particles, in quantum mechanics, quantum field theory. You can pair produce elementary particles in a very strong electromagnetic field. There's the same effect in some sense, analogous to that you have a time dependent, even though the metric looks time independent in some sense. Actually, it's really time dependent as you progress up in time, and that creates particle-antiparticle pairs. The one pair falls into the horizon, and the other pair just escapes to infinity. And the thing that escapes to infinity is what you are usually calling Hawking radiation. Okay, so this is a picture of an evaporating star. Okay, and it also illustrates the fact that there is Hawking radiation inside and outside. The point is that in the end, there is only Hawking radiation and flat space-time. So somebody who is an experimentalist at far infinity will only be looking at Hawking radiation, and it will be thermal, uncorrelated, and therefore information loss. Now, there is a problem with this. So this is his famous 1974 paper of Hawking, this very fundamental paper, in which he quantitatively arrives at the formulas for Hawking radiation. And according to Hawking, once the black hole disappears, it took away the information. And so there's information loss in quantum mechanics. So in fact, Hawking actually was proposing a modification of quantum mechanics. But I think fortunately, it is our understanding of gravity that actually has to be modified to accommodate the verity of quantum mechanics. Okay. So as I said, the final state of the evaporated black hole is only thermal. The information about the initial state is lost. This means mathematically that the final state is mixed and thermal with a von Neumann entropy which is greater than the thermodynamic entropy of the initial black hole, which is absurd. That is not allowed by quantum mechanics, as I will explain to you. Okay, and emphasizing it in a slightly different way, this violates this fact of Hawking radiation, violates a fundamental principle of quantum mechanics, that a pure state cannot evolve to a mixed state in a closed system. See, the closed system is very important, okay? In an open system, many things can happen. The initial and final von Neumann entropy must be zero. So therefore, you have a very serious problem. Gravity leads to information loss, and quantum mechanics cannot allow that. Okay, so this is the point. I hope I have, in some simple way, convinced you that there is a very serious problem about unifying general relativity with the laws of quantum mechanics. Okay. Now you may ask, so what? Okay, in the sense that quantum mechanics applies to very short distances, like the accelerator at CERN, the distances of the order of 10 to the minus 18 centimeters. And gravity is good for large scale cosmology, etc. But we need a consistent theory of quantum gravity to understand the early universe. Not only to understand the early universe, but to understand gravitational quantum fluctuations, which are in some very deep sense responsible for the distribution of galaxies and stars that you really see around you. Also, we need to understand in detail the internal structure of black holes, including the black hole singularity, which we are not going to say anything about because we don't know what is the internal structure. And in some sense, the grand dream would be to formulate a super grand unified theory of all the forces, including the force of gravity. We have unification of weak and electromagnetic interactions and strong interactions, but we've not been able to unify gravity with all those interactions. Okay, so for all these reasons, we need to solve the information loss problem and to see that general relativity is, or theory of gravitation is consistent with quantum mechanics. So I just had these two slides. This is why you need to know the resolution of the information puzzle, because it will teach you about quantum gravity. Okay, I already mentioned all this, and then I also mentioned this, that these fluctuations in the cosmic microwave background, temperature fluctuations, are actually density fluctuations, which are caused by primordial gravitational fluctuations of quantum gravity. This is really a fundamental point, that the shape and structure of the evolution of the universe beyond this photograph over here, which was approximately 300,000 years after the birth of the universe. It's the evolution from here that makes galaxies, stars, all that, has its origin in these primordial fluctuations of quantum gravity. We have to understand quantum gravity to understand and answer some of these big questions of science. I hope I have convinced you. Okay, back to the information puzzle. I'll just give you a very quick, I'll walk you past the history from 1990 onwards. I think maybe it's 1995, I'm not very sure. So one of the important suggestions was, can information loss for black holes be understood as due to an averaging process where there are a large number of internal states? Like, for example, how do you explain in statistical physics the burning of coal? Coal, a piece of coal, let's say 1 kilogram, has a huge number of degrees of freedom, huge, complicated chemical bonds, all types of things. And when you burn it, it just goes into ash plus smoke. You don't jump up and down that there is a problem with quantum mechanics, because you know that if you knew the information about all the things that went off into smoke, you can reverse this system. Not practically, but in principle, you can reverse it. Because coal is described by a Hermitian Hamiltonian. After all, coal plus its surroundings are described by a Hermitian Hamiltonian, so there should not be any problem with time reversal. And you understand why there is temperature, entropy, everything, in terms of what is called coarse-graining of the system. Okay, so this is the old great subject, which was initiated by Clausius and, of course, by Boltzmann, who came up with this fundamental formula. The entropy of the black hole is the constant named after him, which is very small, times the logarithm of the number of degrees of freedom of the system. The question was that, is it possible for us to model a black hole like this? Then we will understand information loss. No need to worry. All right, so the question is, what are the internal states of the black hole that would account for this? So in simple problems, simple situations where the black hole has a large amount of supersymmetry, for example, we have been able to understand this question. And there was very important progress made post 1995, I think 1996, that Strominger and Waffa provided the first concrete evidence in a calculable model that black hole spacetime is a sort of a hydrodynamic description of more basic underlying constituents. Okay? Then Hawking radiation and black hole thermodynamics can be calculated in this framework of statistical mechanics, and this was done by several of us from the Tata Institute and also from across the oceans. But a precise calculation could only be done after the discovery of the so-called ADA-CFT correspondence, and to which I now turn. Means this goes on for many years, and there is a need to formulate a quantum theory of gravity which is not perturbative. That's the main goal. Okay, how do you formulate a quantum theory of gravity? So Maldacena came up with the famous holography conjecture, which says that there is a precise non-perturbative formulation of quantum gravity, but not in a space-time which is asymptotically flat, like the stuff we live in, but a space-time which is like a box. That box is geometrically an anti-de Sitter space-time. Okay, some space-time. It's some hyperbolic space-time. Okay, and you could actually formulate this correspondence. Means whatever happens in the bulk in gravity, like the motion of planets or the collision of black holes or black hole radiation or whatever, has a hologram on the boundary. Okay, and the boundary theory is a good theory. Good theory means it's a unitary quantum field theory without gravity. Without gravity, that's important, which you know how to handle. So in some sense, in principle, all these paradoxes of black hole physics are sort of settled by the ADS-CFT correspondence in principle. Now, here is some beautiful things which Juan had prepared. So here is a illustration of the ADS-CFT correspondence, that there is gravity in the interior, the green stuff, there's some stuff moving around in the gravitational field. And there's a hologram of what happens inside on the boundary. That hologram is something we understand as physicists because it is in terms of gauge theories or theories of which are very familiar with from the theories of elementary particles. So on the boundary, there is a unitary theory. So in principle, there is no information problem in the interior. True, absolutely true. But how do you see that in detail in the interior? That is the question. But before that, how do you describe black holes in ADS? So there's a black hole solution in ADS, which asymptotically is not flat, like the Schwarzschild solution we saw, but is asymptotically merges into ADS spacetime. Now, these are good black holes. They have a temperature, they have an entropy, they have a positive specific heat, so they are good thermodynamic systems, unlike the Schwarzschild black hole, which has a negative specific heat. And you understand how to deal with hot particles in a quantum field theory. So as I said, in principle, this solves the information puzzle because black hole formation is nothing but thermalization of a system in the boundary theory. Now, how does if you have a complicated system in, let's say, some fluids or some condensed matter system, you start heating it actually. So how does it thermalize? Of course, that's not a simple problem to solve. But in principle, it is soluble because you know the Hamiltonian, you know it's a unitary theory. So there will not be any information problem there, and hence there won't be any information problem in the black hole case also because it is the hologram is perfectly good. But as I said, it solves the problem in principle. How does it do this in the bulk theory of gravity? How do you understand that somehow, somewhere, Hawking missed out something, if at all he did, that led to information loss? How do you do this? That's a big challenge, actually. And so it's since 2006, there's a development which was done by a good friend of mine, Tadashi Takayanagi, and Mukund Rangamani, Veronica Hubni, and others, and of course Juan. They started trying to understand the geometric formulation of entanglement entropy or fine-grained entropies of systems on the boundary of ADS spacetime. Okay. So in order to formulate, this is of course post facto, the resolution of the quantum mechanics gravity problem in terms of von Neumann entropy of a quantum system, you have to do it by von Neumann entropy because it's a quantum problem. So what's the definition of a von Neumann entropy? Now this is quantum mechanics. I don't know whether you study it, but quantum mechanics has wave functions and states, right? From wave functions and states, you can form a density matrix. So if you have a certain state psi, a bra, and a certain state, and in its ket, that means its conjugate, then you can form a density matrix. Actually, it's a matrix whose matrix elements are labeled by the elementary or eigenstates of the system. Okay, it has trace 1, and it's a positive operator. Okay, this is an operator equation over here. And the key result that led to all this progress is that people found this this set of people over here, and especially Engelhardt and Wall, found a formula for the entanglement entropy in the context of the ADS-CFT correspondence. So this is a key result. It's a fundamental result. I will try to explain this to you in the next few slides. So this is the point. You firstly discover a certain order parameter or a certain diagnostic of how to ask quantitatively the question of information loss. And that's a von Neumann entropy. Okay. Then you try to develop a formula for the von Neumann entropy in terms of gravitational degrees of freedom, in terms of geometry and the quantum fields in that geometry. Okay. So this is what was done. The initial work is by Ryu and Takayanagi and developed by all these people. Okay. Now let us take I have 2 slides on a tutorial on von Neumann entropy. So I think the idea is that once this lecture is over and you have these slides, you can go and try to solve these few problems in some simple systems, okay? So as I said, the von Neumann entropy is defined by minus the trace of the density of a pure state times the logarithm of the density. Now, this sort of mimics the famous entropy, which we call as Shannon entropy. But Shannon's entropy formula came in 1948, and this formula actually is from the 1930s. Okay, so it's quantum formula to von Neumann. Okay, so it has the following properties. And if you have a pure state, a state which is maximally entangled, then the von Neumann entropy is 0. If there is some loss of entanglement, it will become a small positive number and so on. Okay. The von Neumann entropy is invariant under any unitary transformation. So in particular, if you have a Hermitian Hamiltonian in a closed system, the time evolution operator is unitary, and so the von Neumann entropy is invariant under that time translation. And the von Neumann entropy satisfies a very important bound, that it is always less than or equal to the thermodynamic entropy. There is a logarithm of the dimension of the Hilbert space of this system. Okay, and that is what we call the thermal entropy usually. Okay. Now, these 3 are very, very important simple points. They can be proved rather easily for a system of finite dimensions. N over here is the dimension of the Hilbert space. It can be large, but it has to be a large finite number. Now, number 4 point here is that the difference between the thermodynamic entropy minus the von Neumann entropy is in a sense a measure of the information loss. Okay, you understand why? Because the von Neumann entropy reaches its bound, that is log n, and then this object will be 0. So if it is very, very small, if the difference is very, very small, and it means that there's a lot of information lost. Okay, there are various ways of saying this, but this is the point. Now, if you take a bipartite system like 2 quantum mechanical systems, okay, they can be interacting, they may not be interacting. That's not important. You can prove a very beautiful theorem that if you look at the von Neumann entropy of the union of these 2 systems, is always less than or equal to the sum over here. Now, this is very surprising because it's very different from thermodynamic entropy, right? Because as we know that if you have the sum of the entropy of the parts in thermodynamics is always less than or equal to the sum of the entropy of the whole, right? So in that sense, there's a very deep difference. In fact, I have a feeling that this word entropy is a little bit very confusing because it means very different things in the quantum situation and in the thermodynamic situation. But if we understand what's going on, I just wanted to point out that there's a profound difference between the von Neumann entropy and the Shannon or the other classical thermodynamic entropies. Okay, so that's slide 1 of the tutorial. Now slide 2 is something you can work out at home. So let's take a 2-state system. Okay, system A and system B. System A has 2 states, 0 and 1. System B has 2 states, 0 and 1. And so the dimension of the Hilbert space of system A is 2, of B is 2, and of A and B is 4. Okay. Now you can form many, many states between A and B. Okay. And there are 4 states in this system which are called Bell pairs, okay, for a special reason, which are the maximally entangled states of this system. So I gave a simple example of that. Okay, you take so this state which I've written in that over here 1 upon square root of 2, etc., cannot actually be written as a product of a state from A and from B. Okay, so in fact, there is no way in which you can you can understand the purity of a state of B from a state like this. And if you calculate, now what you do is take this formula, go home, compute the density matrix. It's some matrix, simple matrix, and compute its von Neumann entropy. And you will find that the von Neumann entropy of this state of the density matrix corresponding to the pure state is 0. So we use the word density matrix and the state interchangeably, because if you know one, you know the other. The von Neumann entropy of this state is 0. Trivial. Now, suppose you do not have access to system B, means, that's out of your bounds, like somehow, it's in some other room, and you cannot enter that room. What do you do? What you do is basically you perform a mathematical operation on the previous density matrix. You simply trace over, you express your ignorance of the system B by tracing over the original density matrix, which had von Neumann entropy 0. You do that. Then you recompute the entropy, and it turns out to be log 2. And it's a positive number, not 0. So this is a very simple measure of information loss when you are ignorant about certain degrees of freedom, and you've got to average over them. Or in other words, if you have these two systems and the observer in system B or in system B wants to make an observation, then all that is available to the observer A is just this density matrix and not the original von Neumann density matrix which I presented in the last slide. Okay, so this is a 2-slide tutorial on the von Neumann entropy, and I hope you have some idea of what's going on. And why did I do this simple example? Because of this. So now I explain to you. Now this is a cartoon of a collapsing star. Okay, all right. So a star has come and it has collapsed. So there's a horizon, and it is evolving in time, and ultimately it will somehow disappear according to Hawking. It will still disappear. So here, for example, as I mentioned to you, in the vicinity of the horizon of a black hole, there is a probability to produce particle-antiparticle pairs, just like in ordinary quantum field theory. And over here, one pair goes inside the horizon, so it disappears into the black hole. It's being shepherded along by the gravitational pull into the singularity, and the other one, this A, escapes. So as I said before, this is a very simple example of two-state system A and B, in which the system B is not accessible, and the measurements on system A are only in terms of a certain reduced density matrix, and which indicates to you that information is lost, unless there is some way to keep track of B also by computing the von Neumann entropy. The question is, how do you do that? That's the trick, basically. Okay. All right. So here is the I think this formula on the top for the generalized entropy is it's an endpoint of about 16 years of work since the 2006 paper of Ryu and Takayanagi. So if you see the formula, so let me explain this formula to you. Okay, now just give me a little. So don't look at the formula on the top, but look at the formula at the bottom. So what do you have? You have a ADS CFT correspondence type of thing, in which you have ADS space-time, and there's a boundary in this purple color, CFT D+1. So the CFT always lives in one lower dimension because it's on the boundary. Okay, and there's a certain region A, and there's a complement of that region B. Now the question is, how do you compute the entanglement entropy of A and B? So there is a von Neumann entropy over here. Then you trace over the degrees of freedom of B, and you get a certain formula. But this formula can be formulated very precisely in statistical mechanics, and people like John Cardy and company have done a lot of work on this, and many others. The question was, how do you get a formula in gravity that evaluates this entanglement entropy of A? How do you do that? So this was the great insight of Ryu and Takayanagi. They said that consider a certain surface that goes inside the space-time, inside the gravitational region. Look at the area of this surface over here, the area of this surface X. X is the surface. Let's call the surface X. Now, X is homologous, using the word surface, but it's homologous to the surface A. Okay, homologous means it basically has the same dimension. I mean, if this is two-dimensional, the one that is pulled out is two-dimensional. If this is if A is three-dimensional, then the homologous surface is also three-dimensional. Okay, so you get this surface out. You compute its area. Okay, and you minimize. You minimize means you look at all surfaces and you get a minimum. So that actually computes the entanglement entropy of the conformal field theory. This is a fantastic result, you see, because it's impossible almost to calculate the entanglement entropy of a strongly interacting system in any known way to us, except by the ADS-CFT correspondence. And this is the famous Ryu-Takayanagi formula, which was just the first term of the first formula. Okay, area of X upon 4 times the Newton's constant. I have put h bar c equal to 1. All right. Now, there is a correction to this formula that comes from the quantum fluctuations of matter, which is inside the region bounded by X. Okay, so that's the second piece. Okay, all these pieces got assembled over so many years by all these authors. But this is a review article, but the authors I actually told you in the previous slide. Where did I tell you about the authors? All these fellows, Ryu Takayanagi, Hubni, Rangamani, Maldacena, Lefkowitz, etc. All these people, since all these years, the crowning achievement is this formula. Okay, so now you take this formula and you can compute the entanglement entropy, the leading piece, which is 1 upon Gn, plus order 1 piece, which is just the semi-classical entanglement entropy of matter in this region sigma of X. Okay, you do that and you can compute this. Now, how do you apply it to gravity? So I'll take just a few minutes, 5 minutes more to round up over here. So the application of the von Neumann entropy formula, which I showed you in the last slide, was applied to black hole evaporation in 2 fundamental papers by Almaeri, Engelhardt, Marolf, Maxfield, and Pennington. Every one of these authors is young, except Don Marolf is much older, but all of these other people are extremely young. So, you know, it's progress made by young people. That's quite amazing, actually. So what they did is they coupled the ADS-CFT system to a bath with certain transparent boundary conditions, because you want the radiation to escape. You see, the ADS space is like a box. So if a Hawking photon goes there, Hawking particle, it'll just come back, actually. Black holes don't evaporate in a box. So you just remove those box boundaries in a clever mathematical way and allow the Hawking radiation to escape. Okay, fine. So you were able now to have, you invented a system, ADS-CFT plus a bath, where you can use the von Neumann entropy formula to resolve or to make progress towards resolution of the information paradox. And these people calculated the von Neumann entropy that is consistent with unitarity and quantum mechanics. Okay, and this is just an illustration of their calculation. I just took this slide from Neta's from Neta Engelhardt. So you see in the bottom over here, you have the black hole being formed by some astronomical collapse, actually, gravitational collapse. So you can calculate the entropy in the beginning. Let's say time t equal to 0. According to that formula, there is no horizon. So the area is 0. So the entropy all comes from the fluctuations of matter, which make up the star. So it's just the entropy of the star. If the star came in a pure state, then the entropy, the von Neumann entropy is 0, right? We saw that. Now the point is that what they discovered by this formula is that as time goes on, these two terms compete with each other, the area term and the order 1 term. They compete with each other, and there appears a new extremal surface very close to the horizon at approximately when half the mass of the black hole has evaporated, which actually leads to a formula in which the von Neumann entropy of the black hole and the von Neumann entropy of the radiation also, as time progresses, comes down to 0, so that the total von Neumann entropy of the initial and final state is actually 0, as consistent with unitarity. Now, there's a lot of stuff over here. It's not so easy to understand, but I just wanted to give you a flavor of the solution of something which is going to be, we can see that there's a promise of a solution to a very long-standing problem. And I think this is my last slide. It's about what is called the Page curve. A lot of people are talking about the Page curve. So Don Page was a student of Hawking, I think. And he essentially conjectured, not conjectured, I think he showed, based on simple general principles of quantum mechanics and unitarity, that the Page curve, that black line over here, if you can see it, goes up and down. And this where it starts going down is approximately, it's called the Page time, and it's approximately when half the mass of the black hole had evaporated. Now, Hawking's calculation basically tells you that it's the green line. So the entropy just keeps on increasing. It becomes radiation, it keeps on increasing. And the entropy, the von Neumann entropy of the Hawking radiation when the black hole is evaporated is even greater than the initial thermodynamic entropy of the black hole. And that cannot be right by unitarity or by our theorems of which are implied by quantum mechanics on the von Neumann entropy. The orange line over here is so you calculate the von Neumann entropy of the black hole as a subsystem, and you calculate the von Neumann entropy of the radiation as a subsystem, and both of them actually ultimately go to 0. Okay, so the radiation starts with 0 and goes to 0. The black hole begins with its thermodynamic entropy, or if you like, if you work in terms of the von Neumann entropy, that's the bound of the von Neumann entropy. And so this type of curve was calculated, and by the methods which I mentioned, all these people developed. And this is where the resolution of the information paradox is. And I think one of the main problems over here is to firm up that formula, in the sense that formula has many assumptions, to firm up that formula and to sort of, there is a proposed derivation in terms of wormholes in the Euclidean path integral, which I didn't want to talk about with you. But all that is ongoing work to try to firm up these ideas. But now you see, the important thing here is basically what really is quite fantastic is that black hole information paradox, the mathematical framework of information theory, that is of the von Neumann entropy, has played a very important role. Okay. And we have briefly described the generalized von Neumann entropy formula in gravity, and indicated how it is a good bookkeeping of information. So this is the beginning of a new attack on this deep and fundamental conflict of gravity and quantum mechanics. And every new approach to this problem in the past 45 years has led to new insights, black hole microstates, ADS CFT, and enriched our journey in science in a very broad and beautiful way, because we made connections with lots of other areas of condensed matter physics, fluid dynamics, mathematics, in trying to solve this one big problem. So thank you for listening, and let me end by acknowledging the foundation that supports me, and to Juan for the animations that you saw about black holes, and Stan Whitcomb for the animation of the colliding black holes, and Meta for the few illustrative diagrams which I took from her talks. Thank you very much. Be happy to take questions.
Sir, can you please
Yes,
take a look at the chat box? There are some
just
questions.
one minute. I have to first, I think, get out of this full screen mode. Just 1 minute. Yes. Okay. So I should go to the chat box. All right. Where is the chat box? Where's the chat box?
Stop presenting.
Okay, I'll stop presenting now because
Yes,
I may need to use the slides again to.
sir, are you presenting your entire screen? Then you can just minimize this window and go to the chat.
Okay, I can minimize. Sorry, I am. So should I stop the presentation?
Yes, when it's needed again, then you can present again.
Okay, fine. I've done that. Okay, there are lots of questions here. All right. If the von Neumann entropy is independent of unitary time evolution, is it affected under some non-unitary time evolution? Also, I haven't had a course in quantum mechanics. Would you? Oh, okay. So let me put it as follows. So what I'm talking about is a is a closed system. Means a system which is not interacting with, let's say, what is called an open system, which is interacting with the environment, for example. So in that system, the evolution of the system is not unitary. Okay, because there's dissipation also. Okay, and in that case, the von Neumann entropy of a pure state, there is no pure state. All states are really mixed, and the evolution of this entropy is not given essentially by a Hermitian Hamiltonian, but by what is called the Lindblad equation, which takes into account the interaction with the environment. So this is a very important subject in the quantum mechanics of open systems, to which I think George Sudarshan, also the late George Sudarshan, also made some very important contributions. So is this answering your question? Can you unmute and let me know?
Yeah, I get it. Thank you.
Okay, all right. So how do you experimentally test any of the approaches proposed? What does it mean to experimentally test? So okay, the point here is that this is a contradiction within theory. Okay, Experimentally, quantum mechanics is a good theory till almost 10 to the minus 18 centimeters, right? As illustrated in the, experiments in the Large Hadron Collider in CERN, etc. Okay. Experimentally, general relativity also is a good theory for understanding large scale structure in cosmology, for example, right? Also for description of black holes at long wavelengths, etc. So both these theories have their domain of uh, applicability, but there is a problem. There is a theory problem when you try to combine them. I mean, there are certain predictions of general relativity, like the Hawking calculation, which seems to contradict quantum mechanics. And I think what is happening is that we have not done that calculation in some sense correctly in terms of correct variables. And so this is what we are seeing being sort of emphasized recently. Now, uh, the implication of this type of work for the early universe is, of course, uh, only very indirectly we can talk about. So if you have a good theory of quantum gravity and you're able to compute primordial fluctuations of gravity, then you will see the fluctuations in the sky, in the cosmic microwave background. And I think if you have a fundamental theory, you should be able to calculate all that. There is no theory of the fluctuations in the CMB background. We just take it as given fact with a certain hand waving understanding of the gravitational fluctuations which caused the density fluctuations just uh, before the ionization stopped and the radiation was liberated. The so-called surface of there's a certain word for it. I forget actually, but that's what it is. So I don't see any really direct, presently experimental test of this. It is just a consistency of theory. Does that answer your question or? Hello? Hello?
Sir, his mic doesn't seem to be working. He said it answers the question in the chat.
Okay, okay. So now, Subhadra Maiti. Okay, suppose a pair production of entangled particles occurs in a curved spacetime and two persons A and B. Two persons A and B takes one of them. Now let's say A goes into a smooth spacetime, which otherwise is vacuum. And if the particles are entangled with the particle in B's hand, change momenta or anything? Uh, so I mean, this question is not totally related to any issue of gravity. You're asking about two entangled systems, right?
Yes, sir.
Hello. Can you just detail your question a little bit to me, Subhadra?
Yes, sir. I wanted to mean if some entangled particle or entangled particle pair creation happens at the say near the black hole event horizon,
Horizon. Yes.
and one takes one of them,
Yes.
one of the particles, and goes to infinity
Right.
in asymptotically smooth or flat
Flat
spacetime.
space time. Right.
Then,
Right. Right.
then from his experiment on the A, on the particle he has in his hand, can he say
How do you know something
something?
about the particle that went in? Right.
Sorry, sir, I
Yeah.
didn't answer.
So I understand. So suppose you collect all the Hawking radiation, okay? That is, A collects all the Hawking radiation, right? Suppose. The question is whether you can actually uh, create the state of the black hole from there. That's the question,
Or
really, right?
say anything about the other particle.
Other particle, or yeah, that's right. Now, yes, the answer is yes. The answer is yes. And however, the it's a very complicated measurement that will enable you to do this. And the amount of time it can take to do this would go something like exponential of the entropy of the black hole. Okay, evaporation is fast, but retrieving information by an experiment will take an exponentially long time. And this is a studied problem in this subject and the in information theory. So what happens basically is that this, in order to do this, you will need to create a quantum computer that will, when that quantum computer starts working, it will create an abstract notion of the space-time of the black hole. And it is in this way that I think it will be retrieved. What you're asking is basically, can I reverse the Hawking radiation and find out the initial state of a black hole? That's very difficult to do. But it's possible in principle in a unitary system. This is a difficult question. And in information theory, the process that does this is called a PETZ map, P-E-T-Z. It's the name of a person who has worked in this subject. Hopefully, does it satisfy you, the answer? That it's a very difficult experiment that can enable you to find out the state of the particle B that fell in.
Okay, sir. Thank you, sir.
Yeah. Any other question? How long does it take for an average size black hole to evaporate? Oh, very long time. Let's see. I think black hole evaporation is controlled by this formula that says that the time of evaporation, I forget now. I think if you look at a particle, a black hole of the size of the sun or something, then it takes a humongous amount of time. It goes as, I think, the time. There's something called the Stefan Boltzmann law in thermodynamics, right? Right? That tells you that the evaporation goes proportional to the fourth power of the temperature or something. I forget this. Sorry. If you substitute in that formula all the things which I have said, you'll find that the time of evaporation is very, very large. Some absurd amount for a reasonably sized black hole, 10 to the power of 60 or 64 or something like that. I don't remember just now. But you can calculate it for the weekend. Is there any other question? Yes. You mentioned that in ADS-CFT, the theory on the boundary is unitary, but can we say the same for the internal dynamics? If the ADS-CFT conjecture is correct, the answer is yes. There is every evidence that the answer is yes. Yes, the answer is yes. But there is no real proof for a higher dimensional theory. It's a conjecture. It's like the Riemann hypothesis, much richer than the Riemann hypothesis. Is there any other question? Is this the end of the questions? Yes.
Okay, it seems like there are no further questions.
Okay.
So we would like to thank sir for this very interesting talk.
Okay. I'm happy that I hope I got across. It was not too complicated, but some idea of everything. Something everybody should take home from the talk. Okay. All right.
Sir, there seems to be one last question in the chat if you have
Yeah.
time.
Yeah. Sure. What is it? Ah, in the ADS-CFT, doesn't the hologram version of what's going on in the interior, like looking at the shadow of a bob being circularly spun, like a ball attached to a string? Well, it's a hologram. The hologram is not a shadow. I mean, what is going on here is that if you, for example, uh, let me just let's look at the holographic understanding of black hole formation and evaporation. So, in some sense, when if you have a black hole being formed by the collision of two particles or something at very high energies in the bulk, so the black hole is sort of being formed, and then slowly it sort of stabilizes to have a certain mass and angular momentum, etc. So in the boundary theory, what has happened essentially is that the theory is thermalizing, means it is reaching a state of thermal equilibrium, because a black hole describes a state of thermal equilibrium with a certain temperature, mass, and angular momentum. So it's thermalization that is being discussed in the hologram. I'll give you another example of let's say, yeah, take a black hole horizon. Then particles are falling into the black hole horizon. Sort of classically, information is being lost. What is the signature of information loss in the boundary theory? The signature of information loss in the boundary theory is friction. There is viscosity of the fluid in the boundary. So in this way, there's a very beautiful way you can tie up what's happening in the boundary theory and what's happening in the interior. So I gave you this. This is a very beautiful example of the understanding of viscosity in the boundary theory in terms of infalling particles into the horizon. Does that answer the question? Okay.
Sir, I had one last question.
Sure.
So, sir, I got the impression that, in order to address the information problem, like what the approaches you mentioned, what they did was, in a sense, so when they started with a black hole, and then the analysis was of the evaporation of the black hole.
That's right.
So, is it then, is the question, would the information problem would have also arisen during the formation of the horizon itself, right?
Yes.
Before the black hole existed, and then
Right.
like, is the problem
Right.
addressed in the same way during that period?
Yes. Very nice question. This is something which I have been working on for the last 2-3 years. So that's in some sense black hole formation is the reverse of evaporation, and certainly there is an information problem because the final state of the black hole is a thermal state. Absolutely correct. So the challenge is to start with a with an initial state which is pure of a system and see how it evolves to a thermal state or a black hole state. And that calculation can be done in very simple systems. And you can show that the information problem there has a resolution, but in very simple systems in 1+1 dimension. Yeah, you're absolutely correct. That's another way of looking at the problem and formulating it. And that's correct. Absolutely right. Does it answer your question?
Yes, thank you, sir.
Okay. Okay.
It seems there are no further questions. Again, I'd
Okay.
like to thank you very much for the talk, sir.
It was a pleasure. Great. Great talking to you guys. Okay. Take care.